Hi everyone, in this video we look at coterminal and related angles. So just as a refresher, coterminal angles, if you have an angle that's drawn in standard position, say such as, whoops, let's see here, like, come on pen. Okay, here we go. Alright, we're good to go now. If we draw an angle in standard position, let's call this angle theta. Remember that this arm is called the initial arm, and this arm is called the terminal arm. Now, if we draw another angle, like from the initial arm, as we would in standard position, and let's say that it's 360 degrees past this initial angle. Well, then it would have the same terminal arm, and this angle would be said to be coterminal to theta. Now let's say that we went the other way. Let's say that we went the other way, 360 minus theta degrees. That would bring us to the exact same terminal arm. So this angle as well that I just drew, the one from here to here, would be coterminal as well. And I could keep doing that. I could keep going around, making full rotations about this circle that I've drawn here, and I could keep getting back to the same terminal arm. And all of those angles that are separated by 360 degrees, those are all said to be coterminal angles. So every time that if you take an angle and you add 360 degrees to it, that's what we call or you can also subtract 360 degrees. And you can do that n times, where n is an integer. That's considered to be a coterminal angle. So a related angle, what a related angle is that, remember that we define this thing called the reference angle. The reference angle is this angle here, which we say is phi. It's the angle that's drawn between the terminal arm and the x-axis. A related angle is when you draw that same angle in the first quadrant. So it's when you draw the angle phi in the first quadrant. That's what a related angle is. Okay, so something to note is that so far we've been using predominantly unit circles, I think exclusively unit circles, to figure out what our trigonometric ratios are. But sometimes you'll see an angle that's drawn, and the radius is an arbitrary. The radius of the circle here is not 1. It's an arbitrary radius r. So this has this has unit. This would be r, and this would be r, and this would be negative r, and this would be negative r here. Now, if this point here is x comma y, I just wanted you to recall that I wanted you to recall that the cosine ratio, the cosine of this angle theta, is equal to x over r, where r is the radius of this circle. It's not necessarily 1, that's only for the unit circle. The sine of theta is equal to the ratio of the y-coordinate divided by the radius, and the tangent ratio of theta is equal to the y-coordinate divided by the x-coordinate. Now, sometimes you're not given what r is. R is an unknown value. You might be asked to figure out what r is if you're given x and y. But there's something to note here, is that this makes a right angle triangle. And the magnitude of x gives you this distance, the distance between the origin and this point right here. Now, the magnitude of y will always give you the distance between it'll always give you basically the height of this triangle, or it'll give you the distance from the x-axis to the y value, which is always I guess we call it the height of the triangle. So what that means is that if this distance is the absolute value of x, and this distance is the absolute value of y, we have a right angle triangle. We know that r squared is equal to x squared plus y squared. So if ever we're given x and y, so we're given this coordinate, and we don't know what r is, we can just figure out what r is using the Pythagorean theorem. Likewise, if we're only given the radius, and we are given one of the other side lengths, or maybe we're given an angle here, and we're asked to figure out what x and y are, then we can okay, suppose we're given x and r and we're asked to figure out what y is, we could also use the Pythagorean theorem just to rearrange this. But there's something to note, is that r is always, the radius is always positive, whereas x and y could be either positive or negative depending on what quadrant they're in. So you have to be careful, because the signs of your solutions to this equation, they do matter here. Because let's say you have that r is equal to 5 and x is equal to I don't know, like 3, and this in your angle is drawn in your angle is drawn in this quadrant. Okay, like if your angle is drawn, actually no, that's a bad example, because okay, let's say that x is -3, then, and the angle is in this quadrant, then your solution for y should be negative, because you know that y is negative in the third quadrant here. So that's something to be really careful of. And how you'd write that out is that if you were asked to solve for y, well, you say that 5 squared is equal to -3 squared plus y squared. And you'd rearrange this equation for y. You'd say that y squared is equal to 5 squared minus 3 squared, or minus 3 squared, which is just 5 squared minus 9, or 5 squared minus 3 squared. And so you'd say that y squared is equal to, what is this, 16? And now when you solve this equation, you're going to say that y is equal to the negative root of 16, because it's in, and then you're going to state that it's in the third quadrant, or you could say quadrant 3. Let's use Roman numerals. So you're going to state that it's in quadrant 3, and that's why you've got your y value being negative to this, or your root to this equation being negative. That's something that's really important to take note of. Okay, so let's actually let's leave that. Okay, so in the next problem, we're told to we are told to determine two positive and two negative angles coterminal with 130 degrees. Now, just recall that in order to get angles that are coterminal, we can just add 360 degrees n times, where n is an integer, to 130 degrees. So let's go ahead and we'll do this. Let's say that 130 degrees, 130 degrees plus 360 is 490 degrees. And this angle is going to be coterminal because I've just done a full revolution, which brings the terminal arm back to the same spot. And then I could take 490 degrees. If I want another positive coterminal angle, I could take 490 degrees and I could add another 360 degrees, which is equal to 850 degrees. So these are two positive coterminal angles. If we wanted two negative coterminal angles, we could do 130 degrees minus 360 degrees, which is minus 230 degrees. And then we could also do minus 230 degrees. And we could subtract 360 from that. And that'll just bring us another full revolution, just in the other direction. And then it'll bring the terminal arm back to the same spot. So minus 230 minus 390 is minus 500, or sorry, minus 360 is minus 590 degrees. So therefore, the coterminal angles are 490 degrees 850 degrees, minus 230 degrees, and let me scroll down a little bit, and minus 590 degrees. Okay, so we see that just adding 360 degrees to a given angle takes the terminal arm back to the same spot, and then subtracting 360 degrees would also take the terminal arm back to the same spot. And those angles that are separated by integer multiples of 360 degrees, those are called coterminal angles. In the next problem, we're asked to determine the exact value of cosine of 135 degrees, the tangent of 210 degrees, negative 210 degrees rather, and the sine of 420 degrees. So before we go ahead and do that, let's just let's recall a couple things. Let's recall our special triangles. And I can do better than that. Okay, so if we have a 30, 60, 90 triangle, that probably looks something like, let's say it looks something like this. This is not exact by any means, but okay, let's say that's 30, 60, and 90. We'll recall that the side lengths appear in the ratio of, what was this? This was 1 to root 3 to 2. And for the 45, 45, 90 triangle, and again, that's not great. It should be, let's try to redraw that. Okay, there we go. That's a little bit closer. Okay, so this is 45, 45, 90. The ratio of the sides is 1 to 1 to root 2. So that's important because we're going to use these special triangles to figure out exact values of the trigonometric ratios above. So here it says determine the exact value of cosine of 135 degrees. So let's first off draw this on the circle that I've given you here. And let's suppose that this is the unit circle. So let's suppose that that's 1, and this is 1, and this is -1, and this is -1 here. If we draw cosine of 100, or if we draw an angle of 135 degrees in center position, then that is 45 degrees past 90 degrees. So this angle would be 135 degrees, and the reference angle would be 45 degrees. So something to note is that this is in here we've got a right angle triangle, and this is a 45, 45, 90 triangle. So that means that this distance, first off, since we drew a unit circle, this is has a radius of 1, and since the ratio of the side lengths appear in as 1 to 1 to root 2, we have to find an equivalent ratio. So normally we have 1 to 1 to root 2, but in our triangle here, our radius is, or our hypotenuse is, just 1. So here we would have ratios 1, and since we're dividing by root 2 to find an equivalent ratio, we'd have 1 over root 2 to 1 over root 2 to 1. And here we should rationalize the denominators. We can write 1 over root 2 as root 2 over 2. So we should really write this as, this ratio is root 2 over 2 to root 2 over 2 to 1. And let's go ahead and do that. So root 2 over 2 to root 2 over 2 to 1. And all that I did here was I just multiplied the numerator and the denominators of the fractions that I had before by root 2, the square root of 2. So what that does is it tells me it tells me the x and the y coordinates here. So I know that the x coordinate is negative in this quadrant. So this point right here is negative root 2 over 2. The y coordinate is positive. So the y-coordinate is positive root 2 over 2. So if I want the cosine ratio is the x value divided by the radius. Now the x value in this quadrant is minus root 2 over 2. And the radius is just 1, so I've just got minus root 2 over 2 divided by 1. Now, the question is, do we need to draw this out every single time we want to figure out what the cosine of an angle is? And the quick answer is no, we don't. We only have to think about what quadrant the angle is in. So recall that in this quadrant, only the cosine is going to be negative, or sorry, only the cosine is going to be positive. In this quadrant, all of the trigonometric ratios are positive. In this quadrant, only the sine is positive, and in this quadrant, only the tangent ratio is positive. And that forms the cast rule. And that's based on the signs of the x and the y values in those given quadrants. So let's suppose we want to figure out what I'm going to erase all this for now. So hopefully maybe you've got that copied down. I'll just erase the angles that I've drawn here, because we figured out everything that we want in the first example. Okay, so we have the CAST. And let's think about the angle minus 210 degrees. So minus 210 degrees, we are making a we're going minus 200 or minus 180 degrees that way, or 180 degrees that way, and then we're going 30 degrees past that, okay? So when we do this, the reference angle here is 30 degrees. That's the reference angle. And the angle that I just drew is minus 210 degrees. So I'm going to show you that if you know what the reference angle is, and you know what quadrant your angle's in, you can just think about the special triangles and then include the sine. So I know that the tangent ratio is the ratio of the opposite side divided by the adjacent. Now, what I can do here is, in this quadrant, I know that the tangent ratio is negative. So I'm going to put a negative here. And the magnitude of the ratio of the y value divided by the x value is going to be the same as the ratio of 1 over root 3, the opposite divided by the adjacent in my 30, 60, 90 triangle. So the tangent of minus 210 degrees is equal to minus 1 over root 3. And that's because this distance divided by this distance is, which is going to be positive because we're dealing with distances here. So this distance divided by this distance has to have the ratio of 1 over root 3, because this triangle is similar to this one, because this triangle that I've drawn here is a 30, 60, 90 triangle. So this angle would be 60 degrees and this angle would be 90. So the tangent ratio of minus 210 is minus 1 over root 3, which we rationalize the denominator. And I haven't shown this in a while, but we do this just by multiplying both the numerator and denominator by the square root of 3. So we get that the tangent ratio of minus 210 is equal to minus root 3 over 3. Now let's do, so we can get rid of that now. Now let's calculate lastly, the sine of ratio for 420 degrees. So the sine of 420 degrees, let's first think about what quadrant this is in. So for 420 degrees, we are going we're taking our terminal arm, and from the initial arm, we're going 360 degrees, and then we're going 60 degrees past that. Okay, so the reference angle here is 60 degrees. And what we've done is we've gone, that angle right there that I've just drawn is 420 degrees. But the reference angle, which is really what we're looking for, is 60 degrees. So 60 degrees, notice that here actually 60 degrees and 420 degrees are actually coterminal. Which is really useful here, because I know that for coterminal angles, the trigonometric ratios are going to be the same because they have the same terminal arm. So here I've got a 30, 60, 90 triangle. This angle, let me draw this in a different color so you can see it. This angle there is 60 degrees. So if that's 60, well, that has to be 30. And for the sine ratio, I'm taking the ratio of the opposite side length to the adjacent. So I'm going to go opposite the 60 degree angle, or sorry, not the adjacent, the hypotenuse. So I'm going to go opposite the 60 degree angle, divided by the hypotenuse is going to give me the ratio for this acute triangle, or the trigonometric ratio for this acute triangle. So sine of 420 degrees is the y value divided by the radius, and the y value here divided by the radius is the same thing as root 3 over 2. So y over the radius is root 3 over 2. And the sine of 420 degrees is positive because it's in the first quadrant. All of the trigonometric ratios are positive in the first quadrant because both x and y are positive in the first quadrant.